Hi, everyone. Now we're going to look at permutations from a slightly different perspective, which actually turns out to be easier to compute with and also to provide some insight that you can't see from the kind of more function-oriented perspective that we took up to this point. And that is that we're gonna look at permutations through the viewpoint of cycles. So what's a cycle? A cycle is a particular kind of permutation, and a cycle of length k is a permutation which takes, let's say A1 is one of the elements of our set X. It takes A1 to another element A2. It takes A2 to another element A3, and so forth. And then when it gets finally to this element AK, it takes it back to A1. So you can see why this is called a cycle. You start at some point A1, then you go to A2, then you go to A3, then you go to A4, and then maybe you go on for a long time, and then you go to AK, and then finally you go back to A1. And this is an example of a particular kind of permutation, which is called a cycle. And we have a shorthand notation for it. We just write it in parentheses, A1, A2, A3, and so forth up to AK. That's a shorthand notation for a cycle. If you have a cycle and you don't mention an index, then that means that that cycle leaves that index alone. So for example, if sigma is in S5 and sigma is equal to the cycle 1, 3, 5, that means sigma of 1 is 3, sigma of 3 is 5, sigma of 5 is 1, and the other two elements, sigma of 2 and sigma of 4, get left alone. And if you were to take the two permutations, the cycle 1, 3, 5 and the cycle 4, 2, and multiply them together and then try to figure out in the other notation what that permutation is, first of all, you have to remember that just like with any permutations, you kind of multiply from the right to the left. So if we look at 1, 2, 3, 4, 5, and we ask where do things go, well, 2, we start here, 2 goes to 4, and then the 1, 3, 5 permutation doesn't mention 4, so 4 stays where it is. So that's where this 2 goes to 4 comes from. And 4 goes to 2, and again, 1, 3, 5 doesn't mention 2, so 4 and 2 trade places. And then if we look at 1, 1 goes to 3, well, the second permutation doesn't move 1, 3, or 5. So we can just look at the first permutation. It takes 1 to 3, 3 to 5, and 5 to 1. So these two cycles multiplied together give us this permutation, which moves 1, 2, 3, 4, 5 to 3, 4, 5, 2, 1. So here's another example of these computations. If sigma is the permutation 1, 3, 5, 4, 2, and tau is 3, 4, what's their product? Well, we can do this staying in the world of cycles in the following way. So we're going to start with, let's say, 1. And we're going to ask, where does 1 go? Well, this second permutation, which is the thing we look at first, doesn't move 1. It only interchanges 3 and 4. And the first permutation is a cycle which sends 1 to 3. So the first thing that happens is that 1 goes to 3. Now where does 3 go? Well, the second permutation, which is where we look first, sends 3 to 4, but then the first permutation sends 4 to 2. So the combination of those two things is 3 goes to 4, 4 goes to 2, so 3 goes to 2. Now, if we look at the second permutation, it doesn't move 2 at all. So we just look at the first one, and because it's a cycle, 2 goes back to 1. So you see, the first thing we find is that sigma tau includes the cycle 1, 3, 2. But we're not done, because that's told us where 1, 2, and 3 go, but what about 4 and 5? Well, let's start with 4. The second permutation, the rightmost permutation, sends 4 to 3. And then the first permutation sends 3 to 5. So the combination of 4 going to 3 going to 5 is 4 goes to 5. And then the second permutation, the one on the right, doesn't move 5. So we just look at the first one and we see that 5 goes to 4. And that closes this cycle. So we've managed to write the product of 1, 3, 5, 4, 2 times 3, 4 as the product of cycles. The first one cycles 1, 3, and 2 around, and the second one exchanges 4 and 5. Now, the one observation we can make about cycles is that when you multiply together cycles which are disjoint, they commute with one another. And here disjoint means if you have your cycle sigma, which mentions A1, A2 up to AK, and your cycle tau, which mentions B1 up to BR, if none of the A's and B's overlap, they're complete. Like in this case here, you see 1, 3, and 2 are in the first permutation, and 4 and 5 are in the second. So whenever you have two cycles like that, which don't overlap with one another, then it doesn't matter what order you multiply them together. So in this example, you see what I'm claiming is that 1, 3, 2 times 4, 5 is the same as 4, 5 times 1, 3, 2. Let's just check this in this case. So if we look on this side, where does 4 go? Well, on the left-hand side, we do this permutation first. So 4 goes to 5, and then the second permutation doesn't do anything with 5. So the effect is that just 4 goes to 5. So on this one here, 4 goes to 5. In fact, let's write this in the other notation. It might be easier. So 4 goes to 5. 5 goes to 4, and then this doesn't do anything to it. Now we have to worry about 1, 2, and 3. The second permutation doesn't move 3. The first one sends 3 to 2. The second permutation doesn't move 2, but the first permutation sends 2 to 1. And the second permutation doesn't move 1, but the first permutation sends 1 to 3. So on the left, 1, 3, 2 times 4, 5 is the permutation 1, 3, 2, 1, 3, 2, 4, 5, 5, 4. If we compute it on this side, where they're in the other order, well, now the rightmost permutation is 1, 3, 2. So where does 1 go? It goes to 3, and then the second permutation doesn't affect that. 2 goes to 1, and then the 4, 5 doesn't affect that. 3 goes to 2, but then the 4, 5 doesn't affect that. Now the first permutation doesn't move 4, but the second one sends it to 5. And the first permutation doesn't move 5, but the second one sends it to 4. And if you compare these two things, you see that they're equal to one another. So disjoint cycles can be rearranged into any order. And why is this true in general? Well, the idea of the proof is pretty much what we just went through. So let's compare sigma tau, which is A1, A2 out to A sub k, B1 out to B sub r, and tau sigma, which is B1 up to B sub r, A1 out to A sub k. And let's ask, what is sigma tau of A1? Well, tau of A1 is just A1, because since they're disjoint, none of these B's is A1, and therefore tau leaves A1 alone. So tau of A1 is just A1, and sigma tau of A1 is sigma of A1, which is A2. What about tau sigma of A1? Well, sigma of A1 is A2, and tau of A2 is just A2 because A2 doesn't occur among the B's. And if you use the same argument for any of the A's, I mean, if you did this with A2 or A3, in general, you would see that sigma tau of AI is sigma of AI is AI plus 1. This is assuming I is less than k, because tau leaves AI alone, and sigma of AI is AI plus 1, unless you're at the very end. And tau sigma of AI is tau of AI plus 1, which is AI plus 1, because sigma sends AI to AI plus 1, but tau doesn't move AI plus 1 because tau doesn't mention any of the A's. And then finally, you could check what happens at the very end. Sigma tau of A sub k. Well, tau leaves A sub k alone, and sigma of A sub k is A sub 1, because that goes back to the beginning of the cycle. But on the other hand, tau sigma of A sub k is tau of A1, which is A1, because sigma of A sub k is A1, tau of A1 is just A1 since tau doesn't move any of the A's. Anyway, now you can redo this calculation with the B's, and I won't go through the whole thing, but let's just look. For instance, what's sigma tau of BI? Well, tau of BI is BI plus 1 if I is less than R and bigger than or equal to 1. And sigma of BI plus 1 is just BI plus 1 because the sigma doesn't do anything. And tau sigma of BI is tau of BI, which is BI plus 1, because, again, sigma doesn't move any of the BI's. And you could go ahead and check what happens at the end cases too. If you put all this together, what you see is that sigma tau applied to A1 is A2, which is the same as tau sigma of A1, which is A2. And similarly, sigma tau applied to any of the A's is the same as tau sigma applied to any of the A's. And sigma tau applied to any of the B's is the same as tau sigma applied to any of the B's. So sigma tau and tau sigma do exactly the same thing to the A's and B's. And they fix everything else which isn't mentioned. And so we see that as permutations, they're exactly the same. So checking all these cases shows that sigma tau is the same as tau sigma. And one of the things which is interesting, so this says that if you have a permutation which is a product of disjoint cycles, then the order in which you write those cycles doesn't matter. But what's even more interesting is that any permutation is a product of disjoint cycles. And let me give a couple of examples to show how this works. So here's a permutation of 6 things. And I want to write it as a product of disjoint cycles. And here's the algorithm for doing that. We start with 1. 1 goes to 6. 6 goes to 2. 2 goes to 4. And 4 goes to 1. So when 4 goes back to 1, we've closed a cycle. So what we've captured in 1624 is a part of this permutation. We've sort of the underlined purple numbers. But you see there's a couple numbers that aren't mentioned. So we have to check what happens to the numbers that I haven't mentioned, which are 3 and 5. Well, 3 goes to 3. And that's a cycle of length 1. And we don't write that because if a number's not mentioned, that means we leave it alone. And 5 goes to 5. So again, we don't mention 5. And so what we see is that actually sigma is equal to the permutation 1624, the cycle 1624. Now let's take a look at tau. Again, we start with 1. 1 goes to 3, and 3 goes back to 1. So the first thing that we find is 1, 3. What about 2? Well, 2, which is the first number that's not mentioned, 2 just goes to 2, so we don't do anything with it. So now we've taken care of 1, 2, and 3. What about 4? Well, 4 goes to 5. 5 goes to 6. And 6 goes to 4. So when 6 goes to 4, that closes another cycle. And so we see that this tau is actually the product 1, 3, 4, 5, 6. And one great thing about this is that we already showed that for disjoint cycles, the order doesn't matter. So whether we got 1, 3, 4, 5, 6, or whether we had, for example, started with 4, gotten the 4, 5, 6, and then the 1, 3, that doesn't matter. And this algorithm can be generalized to write any permutation as a product of disjoint cycles. So that's a proposition. Any permutation can be written as a product of a certain number of disjoint cycles. And what's the proof? Well, we start with our sigma in Sn, and we construct the cycles just like we did before. We first take the cycle 1, sigma of 1, sigma squared of 1, out to sigma to the r of 1, where sigma to the r plus 1 of 1 is 1 again. And we let x1 inside the set from 1 up to n be this collection that you get by starting with 1 and applying sigma over and over again. And basically, x1 has r elements. Now we choose an A in the set from 1 up to n, but not in x1. And we repeat this process. So let's call this R2 of A. So this has R2 elements. This is like what we did in the earlier thing. We first picked 1. We took the cycle that contained 1. Then we looked at the elements that we hit. We pick an element which is not in there. Now we take an element B, an A, let's call this A2. Now we choose A3 and so on. But A3 can't be in either of the cycles that we've found so far. And we let x3 be A3, sigma of A3, sigma to the R3 of A3. And we keep doing this, and the point is this can only go on for finitely many steps. Because there's only n elements. And we eventually are going to show that x is x1 union x2 union xs, and these sets are disjoint. So they form a partition of the set from 1 up to n, and even if they were all as small as possible, if they each had one element, there'd only be n subsets that you can do that with. And since if that would only happen if these each have one element, it would mean that our sigma was the identity element. If it's not the identity element, at least one of these sets is going to have more than one element, so there's going to be at most n elements. At most, S is the number of sets in this partition is at most n. And now we have our disjoint, we have our product of disjoint cycles, because sigma is going to be 1 sigma of 1 sigma to the r of 1, and then a1 sigma of a1 this should be 2, I guess, a2 sigma of a2 to the r2. One term for each of these sets where we ignore xi if it only has one element. Because we don't write the cycle if it's only one element. And now you can see that this is actually sigma because these sets are disjoint. And so if you want to know where a particular element, every element of x occurs in one of these sets. And where does it go? Well, if u is an element of x, then u has to belong to xi for some I. because every element of X belongs to one of these things. And that means that U is some power of AI, and sigma of U is sigma to the I plus 1 of AI. So we've managed to partition the permutation. If we want to know what sigma of U is, we just have to look at the cycle that contains it, and we look at where it is, and the next thing in that list is going to be tell us where sigma takes it. So from this, we get every element, everything that sigma does. And so it's kind of an algorithm, and it's essentially the same algorithm that we used to do these calculations.